Okay then, so welcome to lecture number 2. We are revising prob and stats. That's the main ingredient for recent methods like diffusion models, and also the older ones like VAEs and so on. So I am doing some quick revision so that we are all in good shape before we really start those methods. So last time I discussed basic probability, and then today I will introduce random variable, and then distributions, discrete distributions, continuous distributions, joint distributions at some point, then some amount of statistical estimates also is needed, MLE estimates, map estimates. So I don't know how many of you know these things. So that's why I don't assume this. I also don't need that you have to be expert in this, okay, but intuitive idea should be needed, okay. So when I say what is MLE estimate, then you should have some intuition what it means. Based on data, how can I do some estimate, right? Because in real life you only have data in hand, okay. So based on some sample I will approximate something, right? So so I have to go until there, okay, and that's when the actual material will start. And I think with my estimate I will take another 5 classes maybe also. I don't know, depends how it goes, okay. If I have to go until MLE estimate, if I don't assume anything, then it may be another 4 classes, okay. So let's see how quickly we can do this basic stuff, okay. So I'll start with random variable, just to recall random variable, and I will go quickly on these things because it's video recorded. So I assume that you will go home and watch these videos. These video links are there in Moodle, so feel free to watch those videos, talk to me personally, okay. Whenever you have any doubt, feel free to do that, okay. But in this I will go very fast, okay. I will assume that you will cover up these basics very quickly by watching video, okay. Okay, so what are random variable? Random variables are essentially real valued functions, okay. So real valued means that function goes from a domain but then takes real values, okay. So by this we mean real valued function, but sometimes it may not be real valued, it may be vector valued, something like that. So this is called vector valued, okay. Okay, and sometimes it's scalar function, sometimes it's multivariable, so it can go from, in general, Rn to Rm, okay. So multivariable vector valued function, okay. So we can have many scenarios here, okay. So what we are dealing with is a real valued, output must be real. So so let us see an example of toss a coin 5 times, okay. So let's say what is the sample space here, right? If I toss a coin 5 times, then obviously sample space will be 5 okay, possibilities at a time, right? So it's like, let's say tail, 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 tail. That's one possible outcome, okay. So it could be tail, 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 head, or so on, okay. Head, 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 head. So these are the possible outcomes of a coin toss. Then so far we didn't use a random variable, but then in this case my event could be that how many heads are observed, right? So in this case we define some variable, number of heads observed, okay. So in this case what is happening is that I have defined a variable x, and this variable x looks into the outcomes from sample space, and then it gives me some number, okay. So this seems to be of this form, right, real valued. So in this case it's integer valued, but in general it could be real valued. So what x seems to be doing is works on the sample space and then gives me the number of heads observed. So in this case, possibilities for x are 0 or 1 or 2 or 3 or 4 or 5. So it's possible that I can have all 5, possible that I have 0, and so on. Okay. So hence we can define a random variable as a function that we said is goes from x, takes elements from sample space, and it gives me real number as an output. In this case, it's integer. Okay. So that's the concept of random variable. It's a convenience. Okay. Such variable, if we use it's convenient for us. Okay. Okay. So some more examples. Toss a coin 100 times and x number of heads. Again, you can do these exercises. Toss a coin until first head. Okay. And then here x is number of head. Again, x is number of heads. Okay. So these are some of the examples. Now let us classify random variable again into discrete and continuous. So random variables can be discrete. So arguments are similar like we did before, that probability models could be discrete, continuous, and so on. So we can also, like, it's a similar argument here. So discrete, continuous, and mixed. So yeah, so as we say, discrete, we call random variable discrete if the range of the random variable is countable. So if range is countable. Okay. In the continuous case, we will define it in a slightly different way, in the sense that we will define something called CDF. So and then we will say that the CDF function is continuous function. Okay. So in continuous we will deal with it a little bit later, but for the discrete we said the range of this as a function of x. Okay. So what is the range of x? If the range of x happens to be countable, then it's discrete. So for example, in this case the range is countable because the range possible values of that x takes, right? So in this case is 0, 1, 2, 3, 4, 5. Okay. So it's countable. Okay. So we know about random variable. Then there is a concept of PMF. So probability mass function. Okay. So let us say I toss a coin twice, and x is again number of heads. The first thing is, let's say, find the range of x, and second thing is find PMF of x. Okay. So PMF means probability values. Okay. So what it means is that for a given x, what is the probability of that happening? Okay. So in this case I am saying, okay, probability that x equals to 0. Okay. Probability that x equals to 1. Okay. So these are the probability values for that the random variable takes. Okay. So so PMF, we define it to be probability that x equals to x if x is in Rx and it is 0 otherwise. Okay. Okay. So this is the PMF. Okay. X equals to x if x is in Rx and 0 otherwise. Okay. So we are giving some probability values. Okay. So so the probability values, it can be plotted. So for instance, if it's 0, it's 1, 2, 3, and so on, right? So these are the values that x can take. And for this experiment, if I see toss a coin twice, okay, so in this the sample space is head, 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 tail, tail, head, tail, tail. Okay, so this is our sample space, and x denotes number of heads. So in this case, so x values here for us the range of x. When computing a PMF, it's always important to write range first because PMF is calculated for those values, right? So x, range of x is 0, 1, 2, 3. Okay, 3 cannot happen. So maximum because there is only 2 coin here, so at most 2 heads can happen. And now you have to calculate the probability values for these range of values. Okay, so what is the probability that you get, let's say 0 heads? Okay, so 0 head means that this case 0 heads, right? So this means like 1 out of 4. Okay, this is like 1 out of 4. So we are plotting this. Then x equals to 1 means what is the probability that I get 1 head? Okay, so 1 head is this and this. It's like exactly 1 head, not at least. So this is like 2 out of 4. Okay, so it's like half. Okay, this is half. Okay, and then for I get 2 heads, exactly 2 heads. Again, it's 1 over 4. Okay, so again we are here. So we have plotted this, this. Okay, so this is discrete. I should not like make a curve like that, but just to see the pattern. So these are called PMF. Okay, so given a random variable, we calculate the probability. So let us see an example of an unfair coin. Okay, so unfair coin means that the probability is not necessarily half. Probability of head or tail is not necessarily half. So unfair coin means that probability of h is some p that may not necessarily be half. Okay, but obviously p is between 0 and 1. So the experiment is toss the coin repeatedly until first head. Okay, first head is observed for the first time. Okay, so let us define a random variable y is total coin tosses, and then the question is find the distribution of y. Okay, by saying distribution of y, it means that you are supposed to calculate the PMF. Okay, that's what it means by distribution. Okay, okay. So this is an unfair coin p, and then toss the coin repeatedly until you observe the first head. Okay, and y is the total coin tosses that you need until you get the first head. Okay, so y could be 1. You may get the coin toss in the first. You may get the head in the first toss itself. Get in the second one. So the possibilities, the sample space possibilities we see are perhaps we get this, or we get tail and then the head in the second step. Okay, and then we get tail and then head. So this is a case where range of x is not necessarily finite. Okay, so this can essentially keep going, right? So but this is still discrete because according to our definition, Rx must be just countable. It may be finite or it may be infinite, but as long as it's countable, it's fine. So in this case, again, as I say, whenever someone asks you to find distribution, the first step is to write range of y. Okay, that's the first step. So range of y. So what are the possibilities? Okay, so I got head in the first step. So okay, so that's not total number of coin tosses. That was just first one, right? So in the first coin toss itself, I got in the second coin toss 2, third coin toss 3, and so on. Okay, so range of y is natural number, so obviously it's countable. This is a discrete random variable, and yeah, and we are supposed to find the distribution of y. Okay, so meaning we are supposed to calculate the PMF of y. Okay, so probability mass function of y is denoted by py y. Okay, and these are calculated for range of values that y will take. So what we are supposed to find is py y equals to 1, py y equals to 2, and py in general y equals to k. So these are the values we are supposed to find. So what is the probability that I get a head in the first toss? So that will be probability of this event happening. That is already given, right? Probability of head happening is p. In the second case will be this. Since each coin toss is independent, so probability of TH is probability of T times probability of H. So probability of T, because it's only two possibilities there, head or tail, so the other one other event possibility according to axiom will be 1 minus p. So probability of tail necessarily is 1 minus p. Okay, so probability of tail is 1 minus p and probability of head is p. Okay, we use the fact that coin tosses are independent. Okay, so the product comes here. Okay, so 1 minus p. Okay, so similarly we can see the pattern that that for the k 1 minus p, k minus 1 p, right. So this is the PMF. Okay, so now we can make it k as some kind of a variable. We can put a y here and then y here, and then it will look like some function, right. So let us put that, and that will be the final answer in this case. So the PMF, so we can write this as a function. Y is 1 minus p, y minus 1, okay, and p, and y is taking values 1, 2, so on, and 0 otherwise. In PMF value, you necessarily put 0 in the otherwise case, because you know for sure that range has covered all the possibilities, and anything else you just put 0. Okay. Okay. So we know, like for certain random experiments, we know the concept of a random variable, and given the random variable, we know first step is to compute the range, and then from the range we compute the PMF. Okay. So okay. Now what are the properties of PMF? Okay, so property of PMF are essentially properties of axioms basically. I mean, it's implied by those. So remember that random variables themselves are not events, okay, but they encode event in the sense that y equals to y is an event. Just y itself is not an event. Y being y equal to 1 will be called an event where I get an H. Y equals to 2 will be the event when I get head in the second coin toss. Okay, so these are the few things one has to recall. Okay, so PMF values, the probability values, as we know, probability values are scaled between 0 and 1. So hence PMF values are also supposed to be like that, because these are probability values, so they are supposed to be between 0 and 1. Summation over pxx. So since axiom 2 says that the probability of the sample space is 1, so that is implied here. If I sum over all the probabilities for all possible x, then I'm supposed to get 1. And the third one is if A is a subset of range of x. Okay, if you are doing calculations on a subset, then obviously probability that x is in A will be sum over the elements in the subset. Okay, x is in A and the probability values for those x. Okay, so like these are the few properties that we keep in mind. So one thing to note, I mean, these things can be verified here for this example. So sum of the PMF values must be 1. So essentially you have to check here. Sum of the PMF values for all possible y must be 1 here. Okay. Otherwise, you have a wrong PMF. Okay. So PMF is also called distribution. Okay. So distribution must have this property that the sum over all the possible values must be 1. It should not exceed 1. Okay. So in this case also it will be a simple exercise for you to do the sum, and kind of p comes out and y equal to 1 to infinity. So it's a sum of the geometric series infinity, and becomes 1 by 1 minus p, pp gets cancelled and it's 1. Okay. So those things we can do. So sometimes one may ask you to find, so once we have a PMF value, then sometimes we may create an event that says that we want y values within certain range, right? So what is the probability that I get coin toss after the 2 tosses and before let's say 5 tosses. Okay, so what is the probability that I will see a head? Okay, so one can create like many events based on this. So 2 less than equal to y less than equal to 5. So according to this rule, since this A is subset of range of x, so this event A is a subset of range of y. To compute the probability values for those, I am supposed to just sum over the probability values. Okay, so this is basically sum over y equals 2 to 5, and all these values for 2, for 3, 4, 5, all these are here. You can just sum over to get the answer. Now we have seen independent events, and random variable as such has not changed anything. Random variables equal to something is event itself, right? So y equals to y is an event. Okay, it's just a convenience for us. So the idea that 2 random variables are independent just is similar to when 2 random variables are 2 events are independent, that we saw in the last class. So so in the random variable notation, independent random variable means that probability that x equals to x, y equals to y is probability that x equals to x, probability that y equals to y. Okay, so that's how independence is defined. So but that was okay. Earlier we defined in terms of events. So intersection, comma, all this means the same. Okay, this is joint. Okay, and this is also called joint. Okay, so no need to get confused with any notation here. So we have seen before A intersection B is probability of A, probability of B. Okay, but we know that okay, in terms of random variable, x equals to x is A, y equal to y is B, and probability of A times probability of B. Okay, so there is nothing new here. Similarly, what we have seen before, that probability of A given B is just probability of A if A be independent. Okay, so this is something we have seen here, but same thing just applies immediately, right? So I can, in terms of random variable, x equals to x given y equals to y is probability that x equals to x if x, y independent random variable. Okay, so all this just carries over. Okay, so a small quick example on this. So toss a coin twice, and x is number of heads, and find the probability. So we are supposed to use the independence here. So x less than 2 and y greater than 1. Okay, so since and x is number of heads, y is number of heads. Okay, toss a coin twice basically. So toss a coin twice, x is number of heads, and then it says toss coin again, toss coin twice again, and y is again number of heads. Okay, so this is the experiment. I toss a coin twice, count the number of heads, that's my random variable x, toss the coin again twice, and then y is the random variable number of heads, and then you're supposed to find probability that x less than 2, y greater than 1. Now we will use this fact that these are independent events, random variables x and y, because tossing a coin, they don't have any intersection with any sample space. Okay, so they are independent. So this boils down to probability that x less than 2 times probability that y greater than 1. Okay, and whatever we have done, so basically PMF, this was also the same case where we toss a coin twice and we calculated the PMF values already. So this will be the PMF of x with x here, and PMF y is already done. Okay, so based on these two, individually you can calculate probability that x less than 2 and then y greater than 1 and then multiply. So in this case, like y greater than 1, I mean here it's a different case a little bit, because here, so it's not exactly the same. Here, there we will stop at the second, I mean it's not the same basically. Okay, sorry about that. This problem is a little bit different, because here we are tossing until we get the first head, but here what I'm saying is like toss a coin and count the number of heads. Okay, and then toss a coin and then count the number of heads. This is a different problem here, but I'm sure you can do this. Find the range of x. So range of x is first step, is count the number of heads will be 0, 1 or 2, and then similarly for y 0, 1, 2, and then I write the PMF values. Okay, so PMF values, I will look into the sample space, and sample space, if I toss a coin twice, it could be head, 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 tail, tail, head, tail, tail, and so on. Okay, and then for each of these values, I will calculate the probability values. Similarly, I do it for y. Okay, so y greater than 1 here is doesn't mean it's unrestricted like here. Here y stops at maximum y number of head could be 2. Okay, so it's not an unbounded case. So both these can be calculated as an exercise. Okay, now we will go into discrete distributions. Okay, so you may have seen some discrete distributions like so we start with some basic. For the generative modeling, the most important ones are Bernoulli, multinomial, binomial, I mean, and then multinomial, then normal, and so on. Okay, so we get used to that. So discrete distributions. So if you look into discrete distribution, the simplest possible we may think of is that I do an experiment and I get some output, and for other cases I don't get any output, right? So the simplest I can think of is let's say IA is 1 if event A occurs and it's 0 otherwise. So not just like event A, but I would say even point values here. Okay, so 1 if okay, let me give a very precise. Okay, we come to something else later on, but probability of x is a random variable. Okay, is 1 if x is some x and it's 0 otherwise. So we can think of a very simple random variable like this. It takes 1 if x equals to x and it's 0 otherwise, but does it make sense? Like, is it random? I mean, it's just taking point values, right? So either it's if x is x, otherwise it's 0. Okay, so that's the simplest one can think of, but it's kind of not interesting. Okay, we want to go into a case where at least we have two possibilities. So this is not interesting. Okay, so let us look into case where the next simplest one is something called Bernoulli. It takes two possibilities. Okay, so this is the next simplest we may think of. At least I want two possibilities here. Okay, to work with. So it could be like 0 or 1. Okay, it could be let us say pass or fail. Okay, it could be like heads or tail, and so on. So any experiment where you have two outcomes, okay, that can be modeled via discrete distributions. Okay, these known distributions. Okay, the reason why we work with known distributions is that they appear a lot, and many applications can be modeled via these known distribution itself. If not, then we can even mix these known ones and approximate to a very good accuracy, right? So at some point we will see Gaussian models, Gaussian mixture models. I can mix some of the Gaussians in certain way. Okay, just like you take vectors and you mix them, take a linear combination to produce something. In this case, I can take some known distributions, mix them, and I can produce some arbitrary distribution. Okay, so in fact, this is what we will be doing in some sense, right? We will be taking some probability distribution and then looking at some distribution, approximating a distribution of cat, okay, approximating distribution of some text, interesting text, and so on. Okay, so transforming a random variable, this is what this course is about. how well you know how to transform a random variable to what you want. Okay, so that's the main thing. Okay, so that's why we study these distributions, because a combination of these can lead to something interesting. Okay, so so we can define a Bernoulli precisely. So definition of a Bernoulli. Bernoulli is the name of a mathematician, some Swiss guy. So X Bernoulli with parameter P, and then we denote this as Bernoulli. Okay, so this is the notation. Okay, X follows Bernoulli with parameter P. So most distributions come with their parameters. Okay, and with different choices of parameter, they will model different experiments. Okay, and in some sense, you will be doing also, like I have some applications, they follow some distributions, text distributions, image distributions. Okay, which set of parameters or combination of these distributions can approximate those, okay, based on the samples I have, right? So these parameters are kind of the parameters that you may need some way to learn. Okay, so we'll see maximum likelihood and so on, where we estimate these things, okay, based on the data. Okay, okay, so I will come back to this anyway later, but let us describe this. So any distribution has to have PMF. To define a distribution, you will always ask what is the PMF. PMF defines a distribution. Okay, so I must write down what is the PMF. So PMF is P for x equals to 1. So let us say for our convenience, we encode Bernoulli allows two possibilities. Let us encode it 0 or 1. So pass will be 0, fail will be 1, or head will be 0, tail will be 1. Okay, so let us encode those two possibilities like that, and 1 minus P for x equals to 0, and any other value we always put 0, so otherwise. Okay, and obviously P is between 0 and 1. Okay, so so just looking at this, anyone will look at this and say, oh, okay, this is Bernoulli. Okay, so this is how PMF defines a distribution uniquely. And then I can define something called a geometric or why don't I define binomial first? Okay, it's geometric first. Anyway, it's fine. So let us define geometric first, geometric distribution. So many of these initial ones could be understood in terms of coins, right? So for instance, if you want to remember Bernoulli, then I toss a coin, whether it's head or tail. Okay, that goes into Bernoulli. Okay, geometric also can be seen in terms of coin, but now not just once. I will toss it a couple of times. Okay, so until I get a head or something. Okay, so that follows geometric. So already actually we derived that for that y example, 0, 1, 2 up to infinity, right? So we can write that precisely here. Okay, so we can define, so x is geometric with parameter P. Okay, so all distributions have some parameter, so I write this as geometric. Some books you can write just GEOM or something. Okay, so it depends. So geometric P, if the PMF, so we must give the PMF is given by Pxx is P 1 minus P k minus 1, k equal 1 to 3 and 0 otherwise. Okay, so sometimes in books, sometimes you may say that they put P k minus 1 and 1 minus P. It depends, like what are they taking P for? Okay, so whether it's probability of head, whether it's probability of tail. Okay, so depending on what P is defined for and what you are asked for, so whether you are asking for head, okay, probability of getting a first head, or whether in K trials, or probability of getting tails in in first tail in K trial. Okay, so you have to be a little bit careful about the formula. What was the P given? What were you asked for? Whether we were asked for first head or first tail. Okay, so that can change. Okay, so if you can plot these curve. Okay, so you can always plot this because this is a function. So geometric looks something like this. Okay, so you can play around with some Python code or something. You may try to plot these values, and it looks like this. And this is like geometric. So obviously you have this parameter, so you can play around with this parameter, and it can change. Okay, so now we come to binomial, and binomial also can be understood with the coin toss. Okay, so geometric was toss a coin until you get the first head. Okay, where P of h is P. Okay, right. So P of h must be P because that's when you don't have any power, right? So P of h is P. First head case. Okay, so now we can also introduce binomial. Binomial is about how many heads in n coin tosses. Okay, how many heads I will get in n coin tosses. So that's also simple. So we have a binomial distribution, and we write down the PMF directly because it's more or less understood now. So Pxx is okay. So if I toss a coin n times, right? So it's a little bit of a recall of accounting. So these are like n times, right? And then I'm asking how many ways I can get exactly, let us say k heads. Okay, so the parameters for binomial are k and n. Okay, so in this case, how many ways I can have k out of n is n choose k. Okay, so that's why we get n choose k. And then we have pk, so exactly k heads, and remaining are 1 minus pk minus 1. Okay, so you fix that, you get, let us say this guy, this guy, and this guy. Let us say k is 3. So I got head, head, head. Okay, and number of trials is, let's say, 5. Okay, so 5. So I got a h3. So in that case, the probability is p. Okay, so p to the 3, and remaining is 1 minus p. Okay, for the tails. Okay, so and that will be n minus k. Okay, and I'll make a mistake here. Remaining is n minus k. So that will be 3, and then the remaining is 2. And then n choose k is coming for the fact that this h could have occurred in any places. Okay, so how many ways you can rearrange 3h in 5 places. Okay, so that's binomial. And if we plot binomial, then obviously these are approximate plots. So this is for binomial n20, n10, and p is 3, 0.3. Okay, and then if I increase the n, what is interesting is that it goes through this, and this, if you recall, is a bell curve, and bell curve is a synonym for normal distribution, Gaussian distribution. Okay, so and this happens when I increase n. So n equals to 20, p remains 0.3. So this tells me a very interesting fact about distributions that we can already. So if I can already kind of like predict is that if I have if I do my experiments large enough, okay, if my number of experiments is large enough, then it will approximate normal distribution. Okay, and this is one of the fundamental ways people do estimations in statistics. So in general, we are working with big data. Then obviously our n population size is very large, and if our population size is very large, it is okay to approximate it via normal. That's why people study normal distributions more or less a lot more, because they know that they can approximate this via some normal. Okay, and just do estimations based on normal, and then provide some approximate solution. Okay, and there is a proper theorem for that to prove this fact. It's called central limit theorem, okay, and that tells you exactly this, okay. So if n grows, okay, then any distribution given IID, so I see a sequence of random variables x1, x2, x3, x4, and they approach normal distribution, okay. So we can write the statement later on, okay. So this was when I rolled a coin once. I mean, the coin has two sides only. This was the case where coin has two sides and it could be heads or tail, okay. But we can generalize this. You can generalize this to the fact that I'm rolling a die, okay. I'm rolling a die, then I have like k-sided die, then I have k possibilities. So then the next step could be is to generalize this binomial to multinomial case, okay. So then we will just write down the multinomial case, but intuitively we know what it is, okay. It's an extension of the binomial, okay. So let us write down the multinomial PMF. Yeah, before I do that, one more thing about binomial is that it's essentially doing Bernoulli okay, n times, okay. So if I'm doing binomial n times, then it's same as saying that I did Bernoulli, because Bernoulli was like I toss a coin once and I see head or tail, okay, and then I'm saying probability that one head is there, right. But I could have tossed the coin again, okay, second time, and then I'm asking for probability of head or tail. I could have done it n times, and then I would have counted k heads, okay. So Bernoulli binomial is equal to sum of n independent Bernoulli, okay. So this is a lemma. One can prove this. I will not prove many things, so but one can do this: x1 plus x2 plus xn, okay, where xi's are Bernoulli P, and x follows if this is the case, and xi's are Bernoulli and xi's are independent also, okay. So xi's are independent, otherwise it's not possible, okay. Xi's are independent, then x is binomial with n, like how many sum you had, so n, and then p is the same p, okay. So this is a fact that's good to know. Now I will go to multinomial. So multinomial, as I said, in binomial I had a coin with only two possibilities. Multinomial is like you have a die with k sides, okay, and you do the same experiments. You observe one of the possibility of the die, okay, k times, okay, k or p m times or something, okay. So this in multinomial, it's an outcome of tossing a k-sided die, okay, k-sided die, okay. So usually we know like 6-sided ones, but you can generalize this to k-sided, and in this case x now takes a k tuple here and xk, okay. So this is k-sided, so the possibilities are now, it's like a vector now. So so it can do some kind of a one-hot encoding. So am I observing the first one? Am I observing the jth one? So it will be some kind of a one-hot vector. One-hot vector means a vector where you have 1 at the place and 0 everywhere, okay. So here xj is number, okay, number of the side, number of side j of die occurs, okay. So if I roll a 6-sided die, then the first one would indicate whether the one occurred, second one. So if I roll a die, 6-sided die, let us say 6-sided, right. So let us say I had a 6-sided die, I roll it, and then I get, let us say, 3. So the outcome will be denoted as 0, 0, 3. At the third place I have 1, then 0, 0, 0, okay. So this is what it means, okay. If I roll a die and if I get 3, then this is what it means, okay. So with these notations in place, then we can now write the the PMF for the multinomial distribution. So PMF is, in this case, we use mu and then n and theta. Now theta here is also generic now because we may not take a fair die. So if we take a fair die, then let us say six-sided, then possibilities of each happening is 1/6. But we can generalize this. Let us say theta 1 is the probability that the 1 appears, theta 2 is probability that 2 appears, but may not be with the probability 1/6. Okay, so we can have a theta here. So we can write this as n, and then x1 xk, and then product of theta j xj. Okay, j is equal to 1 to k. Okay, that's how we define the multinomial distribution. So theta j, as I said, theta j is the jth component of vector theta. So theta j is probability that side j shows up. Side j shows up. Okay, so multinomial distribution is an extension of binomial distribution. Okay, it's just the notations we are careful about. It's is nothing exceptional here. Okay, and this notation is the multinomial coefficient. Just like binomial coefficient n choose k, we generalize that to multinomial. Okay, so just like define this now, I mean just here so that it's there. So xk is defined to be n factorial by x1 factorial, x2 factorial xk factorial. So this is called multinomial coefficient. So this could be seen as number of ways you can divide a set of size n, okay, into k parts. Okay, so there are multiple applications for this. These are called categorical distributions. The reason why is that it's about a certain number of categories are here. Okay, so most discrete distributions are categorical. They are like 0 or 1. There are like die have like 6 possibilities. So in general, sometimes in probability books they will say let us take a categorical distribution. Okay, that essentially means one of these. Okay, so sometimes we can say in general, like let us say x is categorical distribution theta. Okay, and then main context can be clear depending on what specifically we are trying to use, but all these are part of categorical distribution. Okay. Okay, so discrete, I think we have to do a few more. I think we will go with Poisson next. So let us look into Poisson. So Poisson distribution first, I will write the PMF, and then I will give you some examples of why it's used. Okay, so Poisson. So Poisson distribution, a random variable x is called Poisson. So I call it Poisson. Okay, this is not Poisson, like we do it in, it's a French name. So it's O-N, right? So that's why I call it Poisson. Lambda. So this is how we say x follows Poisson with lambda as a parameter. If its range, so the range of this is 0, 1, 2, so on. So again, it's a countable, the range is countable, hence it's still in a discrete distribution case. And if it's defined to be Pxk is e to the minus lambda, lambda to the k by k factorial. Okay, and this is for k in Rx, and for anything else we put 0 otherwise. So this is Poisson, e to the minus lambda, lambda to the k by k factorial. And k is in Rx, and lambda often denotes some average quantity. Okay, by average I mean like these probability models would model, let us say, like x number of buses come at a bus stop. Okay, between certain time interval is within 1 hour. Then what is the probability that you will get get a bus in next 10 minutes. So it models problems like that. Okay, so maybe I have some example on that. Yeah, there is one example on that. Let us do one very quickly. Okay, so example, number of emails that I get in a weekend can be modeled by a Poisson distribution with average. Okay, so let us do this. So the number of emails that I get in a weekday can be modeled by Poisson. Let us say, as I said, lambda stands for average. So I'm saying like on average. Okay, so with average 0.2 emails per minute. And then the questions are, what is the probability that I get no emails? So probability that I get no emails in the interval of length 5 minutes, in 5 minutes. Okay, this kind of problems can be solved via Poisson. The probability that I get no emails. So you are given an average of a per minute. So lambda will become that per minute, the average. The main thing when you are working with Poisson is to match the scale here. Okay, this average is given per minute and the question is asking for minutes, then you are safe. Okay, but sometimes it may be different. Okay, hour and then you have a minute, then you have to do the scaling correctly. So in this case, let us try to solve this. So the first thing is like we model it. So we know that this kind of problem is like Poisson. So we will take x be the number of emails that I get in, let's say x is the number of emails we get in 5 minutes, and the negation of that will be like no email. Okay, so emails we get in 5 minutes. So let us define this random variable, and then obviously what we are saying is like x is 0. Okay, the problem is asking for no email, so it's like x is 0, and lambda. Yeah, so lambda, since it's being asked in 5 minutes, lambda also has to be scaled with this. Okay, so lambda 0.2 is an email per minute, but the question is 5 minutes, so the average has to be scaled accordingly. So lambda will be 5 times 0.2. Okay, so this will be 1, and then the answer that we have to get is probability that x equals to 0. So probability that x equals to 0 is from the PMF. So probability that x equals 0. So sometimes we write just k, right? But this also means x equals to k. Okay, so I hope you are getting used to all these notations. So what we are saying is like x is 0. So in place of k, I put a 0 here, and lambda we already know. So lambda to the 0 is 1, and e to the minus lambda is 1. So basically e to the minus 1, and k is 0. So 0 factorial is 1. E to the minus 1, basically 1 by e. Okay, this is 1 by e answer. Okay. So this is the sample. Okay, so you can, as I said, in this course only intuition is needed. So you don't think that I'm supposed to do all the problems, I may not be good. It's not needed. Okay, I'm just doing this because you have intuition of what these distributions are. For the course, it's not required that you have to be exceptional. Okay, but knowing what distribution means, that's important. Okay, one can always ask very difficult question. Okay, but that doesn't mean that you don't have the basic idea, right? Okay, so Poisson, there are like many examples. Okay, so another good thing, big thing is CDF. So CDF is, we have seen PMF. PMF is like point wise. So x equal to something point value, what is the probability? CDF means like cumulative. So for x up to certain point, what is the cumulative probability up to that point, right? So we define cumulative. Cumulative is really interesting for the continuous case, okay? Because in continuous case, PMF doesn't make sense. As I said in the last class, probability of finding a number in an interval is always 0, right? So there CDF plays a role, because then you have to define instantaneous change in CDF, cumulative, to get something about PMF, okay, in the continuous case. So then we have to use calculus there, okay. So let us see CDF. In the discrete case, CDF is defined to be, this is a standard notation, fxx, and this is probability, cumulative probability values. So basically x less than equal to x, okay, and for all x in R, in real number, okay. So you can put x to be real number, not necessarily range of x, okay, it doesn't matter, okay, but even if it goes beyond the range or something, it doesn't matter. We define it in a way that everything is fine, okay. So this is cumulative probability values, okay. So in the discrete case, you know, right, how to compute probability up to certain point. So basically you are adding up, okay, all the probability values, okay. So so example, toss a coin twice and x number of heads. So find the CDF of x, okay. So here, yeah, I mean, toss a coin twice, we have already done these things, okay, and x is the number of heads, okay. So we know this is a binomial, okay. So x follows binomial, and let us assume a fair coin. So the p for the binomial will be half. So binomial, that is probability of head, will be half, right? So 1 by 2. So n is the number of times I toss a coin. So here in this case is 2, and p is the probability of head. Then it's half. We assume a fair coin. So in this case, the probability values, if we plug in the formula for this binomial, then it comes out to be 1 by 4, 1 half, and 2 is 1 by 4, okay. And 2 is the max we can get. And then if I have to write a CDF function now, then CDF is fxx, right? So fx, so x values are coming from the range. So x possibilities are 0, 1, 2. Okay, this coin is tossed it twice. So for 0, I need to produce, what is that? So 0. So sum of the probabilities x. So this boils down to probability that x less than equal to x. So this is probability that x less than equal to 0. Okay, so since 0 is included, 1 by 4 will be there. Okay. If x is strictly less than 0, obviously it's everywhere it's 0. So that's fine. Like separately we can write down for that negative cases. So fx is 0 for x less than 0. Okay. So these are like boundary cases. These don't happen, but they just cover it all the cases, right? So for negatives there is nothing to do. For x less than or equal to 0, meaning x is 0, then in that case it's 1 over 4. And if fx, then we consider 1 here, because 1 is the next possibility. Yeah, it's like okay, yeah, I mean the boundary case is fine, but let us see these cases separately. So if x lies between 0 and 1, right? 0 case is covered, okay. So we will consider the case when 0 and 1, I mean less than 1. Okay, so let us do in a way that things are covered well. Okay, so let us keep using this, and then separately we will say what is x. Okay, so if x is between 0 and 1, so 0 less than equal to x less than 1. So if the x is in this range, then the cumulative function will give me 1 over 4, because it will be just probability that x equals to 0 is the case in this range. Okay, and then we can consider the case 1 to 2. Okay, so let us say that, see those cases. So x greater than equal to 1 and less than 2. Okay, so in that case, probability that x less than equal to x is probability that x equals to 0 and plus probability that x equals to 1, right? So this is the case when x is greater than equal to 1 and less than 2. Okay, so this is the case when probability that x is greater than equal to 1 and less than 2. Okay, so I mean it does include the 0 case, because this is always about until that. So essentially it means until 2. Until 2 all possible values. So 0 is included, 1 is included. Okay, and yeah, maybe I'm creating more issues here by giving these ranges maybe. Okay, let's see. Yeah, I mean what I'm trying to say is, like, I just give these values for the reason why we are including all this is to cover up everything, cover all the possibilities for x. That's why. Okay, you can say that, okay, why are you taking values between x, I mean values between 1 and 2 basically, right? Because coin tosses can only give 1, 2, 3 possibilities, but we want to define a CDF that's valid for all the x, all possible real values. Okay, so that's why we are doing all this. Okay, so and then if x is greater than equal to 2, so this is for x greater than equal to 1 less than 2, and if x is greater than equal to 2, then this is fxx, and probability that x less than equal to x, and in this case it's 1, because x greater than equal to 2 case means that I cover up all the sample space 0, 1, 2. So obviously sum of the all those cases will be 1. So now I can write the CDF as a full thing. So combined all this means that it's 0 if x less than 0, and it's 1 by 4 for 0 less than equal to x less than 1, sorry, and it is 1 by 3 by 4 for 1 less than equal to x less than 2, and it's 1 for x greater than equal to 2. So 1 less than equal to x less than 2, it was, we didn't do this calculation, right? So it was 1 by 4 plus half is 3 by 4. Okay, because at x equals to 1 you had half, and until x equals yeah, x equals to 0 you have 1 by 4, so it's sum of these. Okay, so we have combined all this here. Now it looks like a function that does not miss out anything. It's defined on all real numbers. Okay, so x less than 0, it will give you 0. If x is between 0 and 1, obviously we know x will not be strictly between 0 and 1, but even if it is, until then it will be 1 over 4. Until it hits 1 and becomes equal or greater, then it will increase 3 by 4 and 1. So if we plot this, then we see that it will be like a step function, right? Because for certain values it remains constant and then jumps, and then certain value remains constant and then jumps. So that's the way to characterize a discrete distribution, that CDF are necessarily step functions. Okay, so in this case, if we plot, then x less than 0, it's like this, and then between 0 and 1, 0 and 1, it's 1 over 4, so it jumps. Okay, and 0 is taken. Okay, so basically here it's like open, and then here it's 1 over 4. So from 0 to 1 it remains 1 over 4, so it goes like this. So taking the 0 values, and then it's open here until 1, and then from 1 to 2 it becomes 3 by 4. So 1 to 2 it becomes, let's say 3 by 4 is here. It takes these values and goes until here, and then similarly after that it becomes x greater than or equal to 2, it becomes 1. So let us say 1 is here. After that until infinity it remains 1. Okay. So you can see CDF of a discrete distribution is always a stepwise function because it takes discrete values. So it will remain constant for values between those discrete values. Okay, so we have an idea of a CDF for a discrete distribution. Now I will define something called expectation of a random variable. Expectation, as the name suggests, it's about on average what do you expect. Okay, so it's about average. Okay, so when I do a random experiment, I can ask what is the average outcome that I'm expecting. Okay, if I roll a die, then what is the expected on average what I'm going to see. Okay, so let us define this concretely. So it also means mean. Sometimes also it is called average. So x is a discrete random variable, and with the range x1, x2 and so on, and the expected value of x is defined to be like this. So expected value x denoted by ex is defined as follows: is sum of xk, p of x is xk, okay, and k equals to 1 to dot dot dot. Okay. Obviously, for sum to converge, these probability values have to have certain values in a way that if it's uncountable, then this would be a convergent series essentially. Okay, so that's called expectation. Okay, expectation is a linear function. Okay, I mean linear operator. So that helps a lot sometimes. So sometimes expectation is also denoted by mu. So sometimes people write expectations like this, or this is same as like this, and this is same as like this. These are different ways to write expectation. Now given a distribution, we can compute expectation. So let us say x follows Bernoulli, then we can ask find expectation. Okay. So to find expectation, we have to look into this formula. Okay, and PMF values are known for Bernoulli. Okay, and for those values of x, we have to multiply with the PMF values. Okay, and to see what we get. So let us recall the Bernoulli. So Bernoulli PMF was given by p. So px 0. Okay, so range first thing is the range, right? So let us write down the range. Range, since Bernoulli stands for coin toss, the ranges can be encoded as 0 or 1. Okay, so the range of x is 0, 1, and probability of PMF of 0, or let us say had, is 1. Okay, so this is p, and px of 0 is 1 minus p. Okay, these are the PMF values we know for Bernoulli. If it's had, let us say it's 1, probability is p, and then it's still 1 minus p. Now these x values are known. These are the x values. PMF values are known for those values. We have to create this sum to get the expectation. So expectation of x is sum of xk, PMF of x equals to k. Okay, sometimes we write x p sub x k. Okay, these are all the same. Okay, so x, this sum goes for the range of x, right? So I can write this as xk in the range of x. So this is the sum that we are going to do. So first is 0. So it's 0 times probability that x equals to 0. So it's 1 minus p. Okay. So x equals 0 is 1 minus p plus xk is 1, and probability that x equals to 1, it's p. The probability of head, it's p. So overall, the expectation of Bernoulli random variable is p. Okay. So similarly, you can try expectation for geometric, binomial, all those things that can be seen as an exercise. Important thing is expectation is linear. Okay. So linear. So we need to recall what is a linear operator. So expectation is linear. Okay, so expectation is linear, meaning basically linear definition of linearity has to be applied here. So expectation of ax plus b. So according to linearity, a comes out. Expectation of x plus b. Expectation of constant is the same thing. Okay, because if there is something constant, then on average you expect the same constant. Okay, so there is no sense in taking expectation of a constant, because that's a deterministic thing, right? So this is linearity because a comes out, and then sums also split. So x1 plus x2 plus xn, expectation of x1. Okay. So these are the two things that we remember for linearity of expectation. Now we can talk about functions of random variable. So given a random variable, I can have a function of random variable. Okay. So functions of random variable. So function of random variable means that I given an x, I want to get a y. Okay. So that's it, right? Given a random variable x, I will apply some function, I will get a y. Okay. Essentially, this is what we are supposed to do in this course. Given a distribution, I want to get some interesting distribution, and I need to know what is this model that will produce this, right? So in some sense, we are trying to understand all these concepts. Okay, that how transformation happens. Okay, if I'm given a PDF of this distribution of this, how do I know the distribution of this? Okay, this is exactly what we are supposed to do in this course, transformation of random variable. Okay, but doing that requires a little bit of background, right? So a basic question one can ask is, how do you define expectation of y, given that you have expectation of x, given that random variable x is known. So let us say x is Bernoulli. I applied some function on Bernoulli. Let us say function is x square. Can you give me average at least? Okay. Let us say I don't calculate the PMF, because PMF value, calculating PMF value may not be easy. Okay. So let us say I'm given a binomial. Okay. And someone did a transformation of this into this form. Okay. I did a function of the binomial x which became exponential of x. It may not be very easy for me to construct the distribution for this. Okay. I have to go through some techniques, tools. Okay. But at least can you give me the average value that I can expect? Okay. So that is apparently easy. So computing expectation of a function of a random variable is relatively easy. Okay. So at least that I can estimate. Okay. Okay. So in a function of a random variable, the probability values, if I have to compute in the discrete case, if I have to compute, someone will tell me I give you probability a random variable x, and there is a function of gx, and then what is the way that you will construct PMF of x? Okay. So PMF of y, what is the expression that we may have to in the discrete case? Okay. Of course, we have to calculate those. That may not be easy because it involves g, right? So let us first write down. So PMF of y will be PMF of y will be when y is y, and y is when gx. So when gx is y, okay, then we may have to like solve for that. Okay, so PMF of y is when we are asking when is y is small y, and in other words we are asking when is g of gx is y. Okay, so this is the same thing as saying probability that g of x is y. Okay, and what we can do is we can like we can take an inverse here. I can say, okay, this is the same thing as saying that x is g inverse y. Then it becomes something in x, and then I can use x, but obviously I have to know what is g inverse. Okay, so we can write this if g is invertible. Okay, there could be an issue here that g is not invertible. That can be, but if g is invertible, then clearly I can write it is the same as saying g inverse y. Okay, so in this case, if g is invertible, easy to compute, then it's straightforward to find PMF. Okay, because I just do the inverse, because the function is asking for given a y, tell me the value of the probability value. So given let us say some y, let us say 1 or something, I will do g inverse 1, and whatever value comes out, okay, g inverse 1, then I will check x equals to that, and then go back to the x distribution PMF, and then read out the values from there and put the probability values right there. Okay, so yeah, and this is same as saying saying that Pxx for all x such that gx is y. Okay, so this is the same thing. So this is like saying all possible y for which you had the x. Okay, and you need to kind of sum over. So it may not be like a unique inverse in the sense that for a given y I can have a multiple x, okay, for which I can get a gx is y. So what this formula says that you can sum over all those. Okay, so for a given y, find out all those x for which gx was y. Okay, so it's like it can be of this form. If it's invertible, then it's 1-to-1 and non-2. That's the straightforward case. But what we are saying right now is like this, that for a given y, how should I compute the probability values? Then I'm supposed to compute the g inverse y. So then g inverse y could be multiple in case g is not invertible in the classical sense, because invertible means 1-1 and non-2. But this is clearly not the case of this many to 1 here. So g inverse y is this x values. Collect those x values. Okay, collect those x values for which your gx is y. So let us say those x values are 1, 2, 3. So all those x for which gx is y, okay, g of x1 is y, g of x2 is y, g of x3 is y. Then for all those x, in this case x1, x2, x3, I'm supposed to sum. Okay, so that is a way to calculate this. Okay, in case there is no x, obviously it's 0. Okay, because there is nothing to sum. Okay, but if there is, then collect all those, sum it, and so that gives you essentially a template to create PMF for a function of a random variable. But the only difficulty could be in identifying these inverses. Okay, from where x, for which x I'm getting those y. So essentially it involves solving then an inverse. Okay, and we will generalize this idea in a multivariable case. In multivariable case, taking an inverse involves quite a bit, like determinant of a Jacobian and stuff like that. So that's part of transformation of random variable. So we will see that. So yeah, so for discrete case, function of a random variable, we know how to compute the PMF. Yeah. Yes, exactly. Yeah, it is not, but we are taking it in the case of, in the sense of mapping only. Okay, it's like not invertible, but still you want to estimate the probability values, you just take it as a inverse map. Whichever pre-images were there, you just collect those. Okay, but indeed when I write this I'm assuming that it's kind of invertible. So this may be a little bit of misleading notation here, but I see this in terms of inverse map, okay, not necessarily that G is invertible. Okay, so I mean just for a quick example on this, just one example, so that's how we save time. Okay, so X is discrete, a random variable, and PMF is given to us. So this seems to be, yeah, I mean, okay, I mean sometimes it is given even without some experiment. So in this case we don't know which experiment is done, which physical experiment we know about, but it's fine as long as we are given probability values. The PMF sum to 1, it's a valid PMF. Okay, so this is indeed 1 by 5 times is 1 valid PMF. I take it as a distribution. It doesn't matter it comes from some physical random experiment or not. Now X is discrete and you are given a function like this, y is 2 mod x, okay, absolute value of x. Now find the PMF of y. We use this formula here. Okay, so PMF of y, so Py y equals to y is same thing as Py, y is 2 mod x, x is y, okay, and then we have to like do it for various values of y. So let us say start with 0. So let us say y is 0, right? So then we will go back and see for which values of x I will get y to be 0. Okay, so let us say for y equals to 0. Okay, so let us calculate one by one. So y 0. So this is the same thing as saying Py 2 mod x is 0. You see, the moment you put 0, y goes away and problem is solved, right? Then you are asking for which x, 2 times mod x 0, right? So the x values that you get are the k, right? X values are exactly the k values. So which values of k, x 0, exactly 0, right? Exactly 0, 1. So this is the same thing as saying, so remember I do a trick that I change to x now, because now everything boils down to x now, and then only one x is 0, right? This happens only for x is 0, right? Because y is gone. In fact, I can already write x here. Okay, so x equals to 0. Now I read out value x equals to 0. It's 1 over 5. Okay, now yeah, so function is like listing out all possibilities. So one can like list this out for various values. So we don't necessarily have to like do it for all, like just one. Let us say you do it for 4, something like that. So let me do it for 1. Let's say 4. So this is the same thing as 2 mod x is 4. Now we look here. So which of this x, 2 mod x will be 4, right? So in this case it seems like only 2. For x equals to 2, it seems to be, so this is Px and x equals to 2, again 1 over 5. So that way you can list all this and find the PMF of the function of a random variable. And what I was saying is expectation of a function of random variable is pretty straightforward. You don't even have to look for the inverse. So expectation of random variable g of x is given by sum of g of xk. So you evaluate on xk and then you put the PMF values of xk. K equals r. So xk is in Rx. So expectation values are pretty straightforward. You don't have to look into inverse. So I have to compute expectation of g of x. I evaluate on g of x, not just xk like we did in the for x. If I have to do, the only difference is that if I have to compute expectation of x, I don't have this. If I have to compute expectation of function of a random variable, I put g. Okay, that's the only difference. So it's very easy to remember expectation of function of random variable. So here I don't even need to do any example because it's very simple. So expectations can be computed. Next term is something called variance. So variance, I define it So this needs expectation only. So since we know expectation, it's easy. So mu x squared. Okay, so variance of x is expectation of. It's also defined in terms of moment. Okay, so it's like second moment about the mean and so on. Okay, we can generalize this to third moment. I put a 3 here, fourth moment, nth moment, and so on. Okay, so so this is defined to be variance, and sometimes variance gives you more ideas. Okay, so sometimes it may happen that your data may be given in a way that expectation might look very very small, but variance may be very large. Okay. Okay, so on average, you go to a company and company gives you salary of 10,000. So there are 2 employees. One they give 10,000 lowest, and highest they give, let us say, 1 lakh per month. Okay, but the variance is high here. Okay, expectation someone checks, then it will be maybe 10,000 plus 1 lakh is like 55,000 or something like that per month. So you may think that the expected salary is very high, but then you should ask the company, okay, what is the variance? Okay, then you will see there is a big gap. Some are given very small salary, some are given very large. So sometimes variance gives you more idea about the data. Okay, so then so variance, I don't necessarily have to just memorize this, and we will learn as we go. Okay, more about these things. And then there is something called standard deviation. So standard deviation is given like this, and this is defined as square root of the variance of x. Okay, variance of x won't be negative, so square root is justified. Sometimes this formula may not be useful. So what you can do is that you can use the linearity of expectation. You can split this out and apply the linearity, then you get another formula, and this is expectation of x square minus expectation of x whole square. Okay, this is another formula. Sometimes it's useful in this way. Okay, and then some results on like variance. So variance is not linear function. Expectation is linear, variance is not. Okay, so for variance, if I have to apply variance on ax plus b, okay, it won't be like a variance plus b. Okay, so it's slightly different. So let us just recall that. So variance of ax plus b is a squared variance of x. So it's interesting to note that variance of a constant will be 0. You can check from there also. And for a, what it does is that it makes it a squared. Okay, so variance of ax plus b is a square variance of x. Okay, so these are the formulas like you can just keep in mind. And if x1, x2 dot xn are independent random variables, then and x is given to be x1 plus dot plus xn, then variance of x will be sum of the variance. So if xi's are independent, then it's very nice. It acts like linearity. Okay, so variance of x1 plus dot plus variance of xn. Okay, so that's nice. So as I said, IID assumptions will be used a lot later on, and that's not very unrealistic. So we will use this a lot. Yeah, so this discrete is covered. Now we will see whether we will do continuous today. It's already time. Okay, so let us stop here. So continuous we will do tomorrow, and maybe 2 more class. We will go until statistical estimation, and then we will be prepared. Okay, see you.